Representing ratios with tables. So today we're going to look at how tables are another way to represent ratios along with our double line graphs we talked about. So we're going to use tables to represent equivalent ratios. Bitmoji, Mr. Palin, settle down. It's not that bad. So today our things to jot down. If I am looking at a table of values, I know where the rows are and where the columns are. Should already know that a bit from before, but our big things that we're going to look at is when I see a table representing a set of equivalent ratios, I can come up with numbers to make a new row and explain what those numbers mean. So make sure you have all of your information written down and you're ready to move on. Let's talk about some sparkling orange juice. So Noah's recipe for one batch of sparkling orange juice uses 4 liters of orange juice and 5 liters of soda water. So go ahead and jot down a double line graph to show some different sizes with that. So if you jotted down some different line graphs with that, or some different ones, could have done something similar to something like I've got here. Start off with 5 liters. Oops, got those backwards. So we've got 4 liters, excuse me, of orange juice to 5 liters of the soda water. So double batch would be 8 to 10, right? If I kept going, I could easily just skip counting and putting in what I needed to for each spot, right? As long as that ratio still has that 4 to 5 ratio, I could go as far as I need to. What if someone mixes 36 liters of orange juice and 45 liters of soda? How many batches would that make? Well, we talked about just a second ago, 2 batches would be 8 orange juice to 10 soda. What about if I made 36 orange juice to 45 soda? How would that compare? Well, think about it with this much nicer drawn double line graph. To get to 36, how do you go from 4 to 36? Multiply by 9. How do you go from 5 to 45? Multiply by 9. So we make 9 batches of the of this sparkling orange juice if we did it this way. We could keep going on and on with these kinds of number lines, but we start really making a large number line to help us understand things. So let's see how we can do with these. If you had 400 liters of orange juice, how much soda water would you need? 4 to 400, multiplying by 100, so we would need 500 liters of soda water, right? If I had 455 liters of soda water, how much orange juice would I need? Well, I'd have to divide this by 5, right? And then multiply whatever I got by 4. 455 divided by 5 would be 91. 91 times 4 would give me 364. What's the problem with using a double number line for all of these? Yeah, a double number line becomes infinitely large. We start needing multiple pieces of paper to show this out if we're going to draw it out. But thanks to the inventors of table tables, we can make a table. So a table is just another way to organize this information. And what you do with those tables is you have a column on one side, column on the other. And this is where those input-output boxes come into play that you have created in warm-ups and that you've done before. You use the rule that's at the top to help you figure out what's going on. So here, every time, for each one of these, you have to do it times 4. So if we need 100 batches, we have to multiply by 4, right? If we want to make that same thing with 100 batches of or we need 400 liters of orange juice to make that 100 batches, then I need 500 soda waters, 500 liters of soda water to make it equivalent. Once I know the ratio here, when I know how many batches I want to make, makes it a lot easier. It also makes it so that I can figure out other things more simply. Otherwise, I'm drawing something like this, and I keep drawing and drawing and drawing, which there's nothing wrong with all the drawing, but as sixth graders, we want to start getting to using something that's a little more efficient. So let's jot this down real quick. So a table is just something that organizes information into horizontal rows. Horizontal is across, and columns up and down. First row tells you what the numbers represent. So like in this one, this is a very simple one. You're talking about pets and their tail length. So we've got the name of a pet and a tail length. On our previous thing that we were looking at, we had the titles of the two types, and we just had numbers for each of those because we were trying to figure out the total numbers for each. So let's take a look at this here. Let's see if you guys can draw it out and complete this. So we have almonds and raisins in our table here. We have, for this, we have 7 ounces of almonds to 5 ounces of raisins. They've given us parts. Let's see if we can figure out what the missing parts are. All right, well, for me to go to 7 to 28, I have to multiply by 4, right? So I have to multiply this by 4. That gets me 20. To go to 5 to 10, that means I have to double. So 7 next to it's going to be 14. The ratio needs to hold the same across as long as we've got the same things getting represented coming down. 7 to 3 and 5/10. That's half, isn't it? So 5, half of it is 2 and 5/10. 5 to 250, yeah, that's 50 times, right? 7 times 50 gets us 350. 56 ounces, how do we go from 7 to 56? That's times 8. 8 times 5 is 40. So these should be your missing numbers when you got completed. So how did you figure these out? Yeah, well, as you heard me go through and do these, I just looked at how did the number I did have compare back to the original number in that and used it to figure out my other number. Could you have used a double line graph for this? Yeah, you probably could have. And for most of them, it wouldn't have been too bad. But especially when you get here to the 350 and the 250, that gets to be a little bit difficult to represent in the line graph. So sometimes it's easier to use a table instead of a double line graph. Each row of the ratio is equivalent to all the other rows. And if we know one row, then we usually should be able to figure out all the values that go in another row. If we know exactly what goes in one row, we can find an equivalent ratio to move all the way through, as we did back with our trail mix. So we talked about how we know what rows are. That's our ratios, and columns tell us what each of those parts of the ratios are. And if we've got a set of equivalent ratios in that table, that we should be able to make new rows and figure out what each of those mean based on other rows. All right, we're all set.